Welcome back. In this lecture, we will start a new topic. This is the introduction to beta decay. Beta decay is the most common radioactive decay process. It has given rise to elaborate theory, which is quite different from theory of alpha decay. We will look at the theory of beta decay in the next lecture, but in this lecture, we will just get a broad overview of beta decay. So first, let us contrast beta decay with what we covered in the previous lectures on alpha decay. So in contrast to alpha decay, whose energy spectrum was discrete, beta decay's energy spectrum is continuous. So what exactly do we mean by that? So when you have a radioactive decay, there is energy that is being released. This energy released is shared between the products of the reaction, right? So what you see is that when you measure the kinetic energy of the beta particles, which are just electrons, you see that the energy is spread out, okay, from all the way from zero to some maximum energy. Every energy point is present in beta decay. Okay, it is not like alpha decay, wherein some energies were absent and alpha particle had only certain energy levels. So this is a big difference. Why? So one has to understand why is this spectrum continuous in contrast to the decay spectrum of alpha particles. So this maximum energy of beta particles is related to disintegration energy. That is the energy that is released in radioactive decay involving beta particles. So let's try to contrast furthermore. So this is the disintegration energy. In alpha decay, we saw that this Q is shared between two particles. One is the alpha particle, as well as the nucleus that is left behind after the alpha decay, or indicates recoil, because momentum has to be conserved. This moves in the opposite direction, and this moves in the direction opposite to the alpha particle. Okay, so there is a finite recoil energy, and this simplification can be made. We saw this in an earlier lecture on alpha decay. So in contrast to this, beta decay is different. Okay, beta particles are the mass of beta particles are much lesser than alpha particles. So for momentum conservation, there is no need for significant recoil energy. So most of the energy that is released by the beta decay is carried by the beta particles. Okay, so beta max is related to this, and more or less all the energies goes into the velocity of beta particles. Okay, but that is not the reason for the continuous spectrum. We'll see. Okay, so so an important implication of the continuous spectrum of beta decay is that it led to the neutrino hypothesis. We'll see. Okay, so what do we mean by that? So when initially it was thought that when beta decay occurs, there are two products. One is the beta particle, and another is the leftover daughter particle. What is left over after beta particle, beta decay. Okay, so but that's not true. There is a third product which was first hypothesized by Pauli, saying that there is another particle called neutrinos, which are neutral like that of a neutron. However, its mass is more or less zero. Therefore, it's a tiny neutron. That is why it's called neutrino. So its mass is more or less, at that time it was assumed to be zero. We'll see why. But it was later found out that it had a very small mass. Okay. So why was this postulated? Okay. So the reason for Pauli postulating this is this continuous spectrum. When beta particles are emanated from a beta decay, there is beta particles which are very low in energy all the way to high energy. And this spectrum is like a black body spectrum, right? Which is what we gave as an example of a continuous spectrum. So contrast this to the discrete spectrum that was presented in the case of alpha decay, right? So why is this an issue? The why was this surprising, and why? What was the need to postulate the presence of another particle? The reason is that for some conservation, okay, uh, there there is the beta particle themselves have some uh, spin and so on. All right. So for certain conservation rules, there is the typical conservation rules which we are looking at are spin conservation, momentum conservation, and energy conservation. There has to be another particle which has to be generated so that the certain quantities that were constant uh, before that are expected to be a constant before the reaction are also constant after the reaction. Okay, so these conservation rules cannot be um, violated. Therefore, neutrinos were postulated to conserve spin, which is also a form of angular momentum. And then there are other conservation principles, momentum and energy conservation. Okay. So it is surprising when it is said that neutrino have negligible mass. Why is that we are attributing some part of energy to neutrino? And if so, what does this suggest? I mean, the reason why we are stating that is much of the time when we talked about energies in the case of nuclear system, we related energies to E is equal to mc squared. We related energy to mass, and we talked about um, decrease or increase in mass, right? So that's the way we were talking about energy. And if neutrinos have negligible mass, but still are involved in energy conservation, you should ask how that might be so and what is the implication. Already, you know at least one kind of particle which has no mass but still has energy, which is the photon, right? Photon is an excitation of the electromagnetic field. It has no rest mass, but it has uh, energy based on frequency. So, likewise, neutrino were also thought in a the physical nature of neutrino were thought to be similar to that of a photon. Okay, so it has no mass, but still it can carry energy, and it has certain spin. We won't go into these details, but for especially for spin conservation, neutrino were thought to be important. Okay, so this is not very consequential for the rest of the class, so we won't get into the properties of neutrino and few other parity conservation and so on. Okay, but if you take a more nuclear physics class, those issues will be dealt with. But for the important elements of this course, we need not deal with other properties of neutrinos. Okay, so again, when you have a beta decay, as I've emphasized many times over, there is an energetic condition. Okay, the for let's say, beta minus decay, the the products should have lesser energy than the reactants. Okay, so for beta minus decay, when an electron is being given off, what is happening is that uh, neutron in the nucleus is getting converted to proton and this beta minus particle. Therefore, the atomic number of the product is one more than that of the parent of the reactant. Therefore, mass, which is indicative of the energy of the product is less than the energy of the reactant. That is the energy constraint for the beta minus decay to be spontaneous. Then you have a beta plus decay. This is a positron. Positron has the same mass of that of an electron, but a positive charge. Okay, so these are all the implications of Dirac's theory of particle-antiparticle, of relativistic quantum mechanics. We won't go into that, but we just state that there are antiparticles that exist for every particle. So positron is the antiparticle of electron. Okay, so this the energy constraint equation has a certain feature, and this feature can be elaborated a little bit. So okay, so when you have a positron, what is the product? So a positive charge has emanated from the nucleus. Therefore, the atomic number goes down by 1. So this is indicative of the product nucleus. So because one of the particle that has come out is that of that is the positron, has a mass that is the same as electron. So out of this two ME, one of the ME is that is mass of the electron is the mass of the positron that is being emanated. That positron gets annihilated with the reaction with an electron. Okay, so the other Me we add here because of the annihilation of the positron with the electron. Okay, so this is this is indicative of the energy of the leftover nucleus, the one of the product, and the 2 Me is 1 Me corresponds to M sub E. M subscript E corresponds to mass of the positron, and the other Me corresponds to the electron that is annihilated because of a positron emanation. So this is the energy constraint of for the positron decay, and you have electron capture. In this, some electron, typically from the inner shell, falls into the nucleus, let's say, and when an electron falls into the nucleus, in a way it reacts with a proton to generate, let's say, a neutron. Therefore, the atomic number has to go down. So this is indicative of the energy of the product. So the energy of the product has to be less than the energy of the reactant. Okay. So when we say beta decay, we are not only talking about this. This is the form that probably you have been exposed to from your high school days. But there are two other forms which are also quite important: positron decay as well as electron capture. And for all these three, the typical energy constraint, that is the energy of the product has to be less than the energy of reactants, has to be obeyed. So typically beta emitters can, the energy of beta emitters can range from kilo electron volts to even 15 MeV. Okay, so there's a wide spread in the energies, which are also indicative of widespread uh, in the half-life period. Okay, so we in the previous lectures we have already talked about how energy is indicative of kinetics, and if there's a widespread in energy, then you would also anticipate widespread in half-life. So, for example, these kinds of emission might have very small half-life, and these kinds of emission might have very large half-life. Okay, so we will talk about this relationship in time. So most often, the beta emitters do not have energies greater than 4 MeV. Um, so because beta particles are very light, if they have to have a lot of energy, the energy goes into the velocity, right? You have to have fairly high velocities. So the velocity can reach quite close to that of the speed of light. So because of all these reasons, the the motion of beta particles have to be treated relativistically. So, like the way we talked about alpha particles, you can apply a magnetic field, and the beta particles will have a circular path because of Lorentz force. And the nature of such trajectories give you an idea of not only the charge of the particle, and it also tells you a few other things. Okay, so mass and so on. We won't go into that, but this relationship is obeyed, where H indicates the magnetic field, R indicates the radius of the circular path, and beta indicates the usual rotation which we use in uh, special relativity. There is velocity of the particle divided by speed of light. This is a beta particle, and it can we showed that the kinetic energy of beta particle is related to is given by this relationship. Again, we are not going to derive any of this, but you should be aware of some of these implications. All it suggests that if you want to understand nuclear science and engineering more deeply, um, greater exposure to quantum mechanics and some aspects of at least special relativity is useful. So, in the next lecture, we will take up an elaborate and a fantastic theory developed by Fermi to explain beta decay. That is often referred to as the Fermi theory of beta decay. That'll be the topic to be discussed in the next class. Thank you.